Okay, we've talked about forces, and the simple relationship between force and energy is that the work done by a force is equal to the force times the distance over which that force acts on an object. So I've got a spring scale here and a little cart on wheels, and when I just let that be suspended, we can see that the gravitational force exerted on this cart is a little bit over 9 newtons. It looks like 9.5, 9.25 newtons. Really, that's the force that the spring on the back of this is pulling up on the block, and since the block is not moving, that must equal the force that gravity is pulling down on this thing. So right now, there's no work being done on this because it's not moving. There are two forces acting on it and they're in balance. But if I take this from the ground, and I've just got it suspended there, and it's about 9.5 newtons, and I lift it up by a distance of, say, 1 meter, then I've done 9.5 newtons times 1 meter of distance, or 9.5 newton meters, which is 9.5 joules of work. So I just did some work on this cart. Okay, took me 9.5 joules of energy. I'm going to have to go have a sip of Coke to make up for that. So that's a certain amount of energy that's gone in there. Now the force that was overcoming, that I was working against, is the force of gravity, which is pointing down. If we were floating in free fall and not having to worry about working against gravity, then this scale would show 0, not 9.5 newtons, which means that it would take 0 force for me to move this thing, and therefore no energy to move it. To show that that amount really does vary with the direction that you're going against the force, what we're going to do is measure the amount of work that we do, whether we're going directly up against gravity or at an angle. So the top of this ramp is at 100 centimeters or 1 meter, which means, as I've just demonstrated, when I lift it straight up off the floor, I've done 9.5 newtons of force times 1 meter of distance, or 9.5 joules of work. Now, if I take the cart and put it on this ramp, to move the cart up the ramp, it only takes about 6 newtons of force, and that's because I'm not working directly against gravity. I've got some support from the ramp itself that's helping keep it up against gravity. So I'm only having to do 6 newtons. So if I pull it all the way up here, at the top of the ramp now, this cart has the same gravitational potential energy as if I had picked it straight up from the floor. So it's got to have the same amount of energy, which means I must have put the same amount of energy into it to get it to the top of this ramp, whether I lifted it straight up from the floor, which we already calculated was 9.5 joules, or I drag it along the ramp. Well, dragging it along the ramp with 6 newtons of force, let's see what the distance was. It is 150 centimeters. 6 times 1.5 is 9. So again, I get to this 9 joules of energy to bring it up the ramp. Whether I go up the ramp, it's 6 times 1.5, or straight up from the floor, it's about 9 times 1. So I've got the same amount of energy to get it there, no matter which way I go, up or down the ramp. If I don't pull against gravity at all, then we can see that the amount of force required to pull the cart against no gravity at all with wheels, and there's very little friction, the scale reads 0. So I'm not doing any work at all to move this thing along here, just a minuscule amount that we can't measure with this sort of tool against friction.